Good afternoon, HVAC team. Today we are jumping into Unit 12, and Unit 12 is about the refrigeration cycle, and that's one of my favorite topics to discuss because that's the essence of what we do. As a refrigeration technician, we need to get a good handle on what the refrigeration cycle is and what it does. So let's go ahead and jump into it. So the objectives are explain the fundamental principles behind the refrigeration cycle, identify the four major components of compression cycle, or of the compression cycle, name the three main refrigerant or refrigeration system interconnecting lines. There's three, and then identify where in the refrigeration system the refrigerant is saturated, superheated, or subcooled. The reason why I said there's three a second time was because for a long time I thought it was just the two lines, and there's a third line that doesn't get a whole lot of attention, from a lot of, at least from the people that taught me. So we're gonna make sure we cover all of that, and then also draw a basic compression refrigeration cycle and identify the pressure, temperature, state, and heat content in and out of each component. So I believe that was a project that everybody already did, or it's assigned to everyone. Obviously, we're not going to draw right now, but we will discuss all the components. So compression refrigeration. The mechanical vapor compression refrigeration cycle is used in many types of HVAC systems. A thorough understanding of the refrigeration cycle is absolutely essential to working in the HVAC field. It can be found in all sizes of systems, from small dormitory refrigerators to large industrial chillers. The compression cycle has been used for a diverse range of applications, including air conditioning, commercial refrigeration, and industrial process refrigeration. Subcooling. Superheat and subcooling are two concepts that you're going to hear over and over and over again. Those are two measurements that we lean on to diagnose the system. We're going to cover it a lot. It's something to pay attention to. Even my graduates, I always make sure I refresh them on what superheat and subcool is, because those are two concepts that you'll probably get quizzed on in interviews. I've had it done to me where they've asked me to explain what superheat and subcool is. So you definitely want to be able to explain what superheat and subcool is. So starting with subcool, it is desirable to subcool the liquid refrigerant either either in the condenser or in the liquid line before the metering device. Subcooling the liquid refrigerant reduces flash gas and increases mass flow. So they didn't really get too deep into subcooling, but subcooling is removing the heat from the liquid refrigerant and basically ensuring, like, without a shadow of a doubt, that there's no more vapor present and it's all 100% liquid going into your metering device. So you're basically, it's cooling the liquid refrigerant below its saturation point. So it's already below its saturation point. It's already condensed from vapor to a liquid. And then we're going to remove even more heat energy just to ensure that there's no vapor present. It's all been completely 100% condensed to liquid so that we could send 100% liquid into our metering device. So that's the point of subcooling. When you check your subcooling, and if it's not correct, then that's letting you know. If you don't have enough subcooling, then that's letting you know that your refrigerant your refrigerant in fact has not all condensed to a liquid, and it's probably due to an undercharge. Probably due to an overcharge. So you just want to be careful about that. But that's the point of subcooling. We want to make sure we got 100% liquid going to our metering device. Excuse me. Compressors. The compressor is a mechanical device for pumping refrigerant vapor from the low pressure evaporator to the high pressure condenser. The main types of compressors are reciprocating, rotary, centrifugal, screw, and scroll compressors. So the compressor is the heart of the system. It's what pumps the vapor refrigerant through the system. And it's a vapor pump, not a liquid pump. Can't stress that enough. You can't compress a liquid. If liquid gets in your compressor, you're gonna break your compressor. So it's a vapor pump. It's the heart of the system, and it's one of the two dividing points of the system between the high side of the system and the low side of the system. Just like what it said here, it said that it pumps refrigerant vapor from the low side of the low pressure evaporator to the high pressure condenser. So you got low pressure vapor coming into it, it compresses it, shoots it out of the discharge line as a high pressure, high temperature vapor. Heat flow. Heat is always trying to reach a state of balance by flowing from a warmer object to a cooler object. Heat only flows in one direction, from warmer to cooler. You'll hear me repeat that all the time. That's one of the laws of thermodynamics. Heat flows from hot to cool. Heat flows from hot to cool. It doesn't go the other way around. If you touch something and it feels cold to the touch, that's because you are warmer than that object. And if you hold on to it long enough, the heat energy is going to leave your body and attach itself to that object till it gets to a point where it's balanced and your hand is the same temperature as that object. That's when the heat flow will stop. The two factors that affect the quantity of heat transfer between two objects are the temperature difference and the mass of the two objects. Temperature difference is what allows heat to flow from one object to another. The greater the temperature difference, the more rapid the heat flow. The condenser. So we already covered one of the four components. So let me backtrack. There's four major components that make up the refrigeration cycle. There's a whole bunch of other components that gets added into the equation, but those are all considered accessories. But there's only four key components that are necessary to actually have a refrigeration system. Without one of those four, you don't have a refrigeration system. You will not be able to complete the refrigeration cycle of removing heat from one place to another place. So you got to have all four. So we cover compressor, which is the heart of the system. That's one of your four components of a refrigeration system. And now we're moving on to number two, which is the condenser. The condenser is a device for removing heat from the refrigeration system. The condenser de-superheats the refrigerant. The condenser changes the saturated vapor refrigerant into a liquid. The condenser subcools the refrigerant. The first portion of the condenser cools off the superheated gas and lowers its temperature to the saturation point. This part of the condenser is called the de-superheating section. When the temperature of the vapor reaches the saturation temperature, the additional latent heat removed causes condensation of the refrigerant and producing liquid refrigerant. The end of the condenser subcools the refrigerant, lowering the refrigerant temperature below the saturation point. This is called the subcooling section of the condenser. So the condenser is like a radiator. It's just one big coil, one big copper coil with these aluminum fins that are there to direct the airflow, across the coils and promote good heat transfer. So it's one, they described it in three sections, but it's one coil. It's not physically broken into sections, but they're just kind of giving you a guideline. Like basically in the beginning of the condenser, starting to subcool the the vapor refrigerant. And then as it goes through, like midway through the condenser, it starts to condense into a liquid. And then at the end, coming out of the condenser, it should be 100% liquid. The remainder of the heat that's being removed is subcooling the liquid, so that's the subcooling zone. How is this heat being removed? The condenser fan. They're not getting super duper deep about that in this PowerPoint, but I'm just big on understanding how things work. So the condenser coil, again, is just like a radiator. It's just a big copper coil with the aluminum fans going across it, and it's getting pumped full of hot vapor. What's removing the heat from that vapor is the condenser fan on top of the condenser. So as the condenser fan turns, it's drawing in the outside air because the condenser is located outside. So it's drawing in the outside air across the coil. And like we talked about earlier, law of thermodynamics, heat energy travels from hot to cold. So if the outside air is colder than that hot vapor inside the condenser, when that outside air comes across that coil, the heat transfer is going to take place. So now the cooler air that's coming into the coil is getting sucked in by the fan on top and getting blown straight out the top. So the outside air comes in and flies straight out the top. So it's coming in cool, heat transfer takes place, it's absorbing the heat from that refrigerant and blowing it right out the top. That's why when the air conditioning is running, if you go outside and put your hand over the condenser fan, you'll feel warm air blowing against your hand. That is literally the heat energy that was in the refrigerant being sucked right out through the top of the condenser. Because again, heat transfer goes from hot to cold. Cold air comes across that coil, the heat will transfer from the refrigerant to that air, and that warm air gets blown out the top. So as the heat is being removed, the refrigerant is traveling through the coil. By the time it comes out of the exit of the coil or the outlet of the coil, that fan's been turning, doing its thing, and all the heat is being removed, and it's coming out as subcooled liquid. So that's how the heat is being removed. I think some of the explanations need to go together. This chapter is not talking about condenser fans, but I feel like it was necessary to mention because they're just talking about de-superheating like this is just some automatic thing that happens just because you're in the condenser. What happens because the condenser fan is pulling the cooler outside air across those coils, and the heat transfer takes place, and then that heat that is transferred from the refrigerant to the air is now blown out through the top of the condenser and just released into the atmosphere, which is another reason why the condenser goes outside, because we're removing heat from inside and we're dumping it somewhere where it doesn't matter, which is outside. We don't care. It's already hot outside. So we're dumping the heat out there and we're removing it from inside so that we can be comfortable indoors on a hot day. Excuse me. All right, moving on. Air-cooled condensers consist of three types. You got natural draft, forced draft, and induced draft. And then there's also water-cooled condensers, open vertical shell and tube, shell and coil, horizontal shell and tube, double pipe. Water-cooled condensers use water to remove the heat from the refrigerant rather than air like the one I was just describing. And it comes in different forms. The ones that that's most common is the double pipe, where you have the refrigerant pipe and then you have a water pipe around it. So as that warm refrigerant travels through the pipe on the inside, the cooler water that's flowing through the pipe on the outside is absorbing the heat from that warm pipe, because again, heat travels from warm to cold. So all the heat that's in the refrigerant is now in the water, and that water is being, is flowing. So it's coming in from its source and it's flowing out. And you got that constant water loop. The cold water is going out, and or the cold water is coming in, absorbing the heat, going out, coming back in, cold, absorbing the heat, going out. So that is a different setup. You'll see that on like water source heat pumps and things like that. But the most common, I would say, is the air-cooled condensers. Evaporative condensers. Evaporative condensers use water evaporation to help cool the refrigerant. Evaporative condensers also require more maintenance than air-cooled systems because the warm water sump is a perfect place to grow bacteria, mold, and fungus. Also, evaporation causes mineral scale to build up. If the scale is not removed, the condenser's efficiency will drop. So cleanliness is a huge thing in our field too. Evaporative condensers get, you know, bacteria, mold, and scale buildup, but then also air-cooled condensers get all full of dirt, dust, and leaves and debris and compost and stuff. So maintenance, routine maintenance is important. It's often overlooked and undervalued, but by consumers and also by lazy technicians. I ain't gonna lie, I'm one of them. I've had days where I just didn't feel like, you know, doing it. I mean, honestly, I hate doing maintenance. Service calls are a challenge. When you figure it out and you get it fixed, you get a rush. You know what I mean? Maintenance is just work. You know, there's no reward, there's no excitement. It's just work. It's just monotonous, repetitive, dumb work, but it's necessary. It's extremely necessary, especially as a business owner. You want to develop a working relationship with your customers. You want them to understand the importance of it, and you want to basically take on your customers' equipment like it's your own. Like you're coming in and you're making sure your stuff is working right, so that they're comfortable. So, and also it's a revenue stream. I mean, routine maintenance is where, you know, where a lot of the companies make their money. That's where the bread and butter is. That's your opportunity to go in and find work, see what's you know, what needs to be fixed, what needs to be done, what upgrades might need to be recommended. So maintenance is very important, and it is also very boring, but it needs to be done. And anyways, clean systems are efficient systems. If they're all dirty and toe up, they're going to have to work twice as hard to do their jobs. So anyway, the meter. A metering device controls the flow of refrigerant to the evaporator. It separates the it separates the high and low pressure sides of the system. Two actions occur in the metering device. One, the pressure of the refrigerant is reduced to a pressure corresponding to the evaporator temperature at a saturated condition. And two, the refrigerant liquid is cooled to the evaporator temperature by actual evaporation of some of the refrigerant liquid. All right, so number one, it's where it drops the pressure. So how I said earlier, the condenser is one of the two dividing points in the system. Well, the metering device is the second one. The compressor is taking the high pressure vapor and turning it into it's taking low pressure vapor and turning it into high pressure vapor. The metering device is taking high pressure liquid and turning it into low pressure liquid coming out of the other end. And then what else? Oh, and then as far as what was the second one? The refrigerant liquid is cooled to the evaporator temperature by actual evaporation of some of the liquid. So basically, the moment that the refrigerant goes through the metering device and lowers the pressure, it also some of the liquid automatically flashes into a vapor. So this is what gives you that third line. So at some point they're going to get into the three lines. I'm just going to jump ahead. You have your liquid line, which is the outlet of your condenser, because remember, your condenser took the high pressure vapor and then it spit out high pressure liquid. So now you got liquid coming out of the condenser into your liquid line. And then you have your suction line. The suction line is that vapor line that's going into the inlet of your compressor. That's the low pressure vapor that's going into your compressor. But that third line is the transphase line. And that's what's coming out of your metering device. And it's called the transphase line because the refrigerant exists in two phases at once. It's coming through it's going into the metering device as liquid, and it's coming out 25% vapor, 75% liquid. And it's referred to as a flash gas. And again, that's happening because of once it goes through the metering device, some of the refrigerant immediately flashes into a vapor. So you got your flash gas in your transphase line. And that's also number 3. out of your 4 key components to make a refrigeration system. So we had our compressor, we had our condenser, and then we go from the condenser to our metering device, and then we're going to come from our metering device into our 4th component. But so some more on metering devices. There are 2 major types of metering devices commonly used in modern refrigeration systems: fixed bore expansion devices and thermostatic expansion devices. So they're flipping around, they're switching up words on you. The first one called it a meter, then they started using the term metering device. Now they're talking about expansion devices. All the same thing. It's the same thing. There's 2 types, 2 main types: your fixed bore, or sometimes referred to as fixed orifice metering device, which is basically is going to be either a piston or a capillary tube. But basically, what it is it's a it's non-adjustable. It's a fixed size. A capillary tube is just a really skinny pipe, and so the size of the pipe coming into the metering device is going to be a lot larger than the cap tube itself. It's going to, you got, let's say a 3/8 inch pipe, coming into the metering device. It's going to reduce to a tiny, skinny little, I don't even know the measurement, skinny little pipe. And that size change is going to create a pressure change. And it's a non-adjustable. That whatever size that cap tube is, or however long that cap tube is designed to change the pressure, to drop the pressure a significant amount, and that's it. That's all the adjusting that it's going to do. It's just basically based on going from a larger pipe to a smaller pipe. Same thing with the piston. They call them flow rater pistons or just a piston. Another type of what's considered a fixed bore metering device. Again, you got the refrigerant coming in, in a larger pipe, and then it's going to go through this tiny little orifice in the piston, and that's going to create your pressure difference. The TXV, or the thermostatic expansion valve, that one is adjustable. So the amount of refrigerant that's coming out of it is not just based on going from a big pipe to a smaller pipe. It's coming from a bigger pipe and then going through the metering device and coming out in a smaller orifice, but the amount of refrigerant that's allowed to come out of the outlet of the TXV is based on the load on the evap coil. So I might be getting a little bit ahead, but basically there's going to be what's called a sensing bulb that's going to be on your suction line. And that sensing bulb has a small amount of refrigerant in it, and that refrigerant is going to, depending on the temperature of the suction line, that refrigerant is going to either evaporate and become vapor. And then, so the more vapor that's in that TXV is going to put pressure on the diaphragm, and it's going to open it up and allow more liquid refrigerant to flow. If the suction line is not that warm and the refrigerant inside goes back to a liquid inside of the sensing bulb, then that vapor pressure is going to relieve off of the diaphragm inside of the TXV, and it's going to close a little bit. It's going to allow less liquid refrigerant. So anyway, I might have went too deep. There'll be a lot more on TXVs in later modules, but just getting back to the basics, the fixed metering devices, or fixed bore or fixed orifice, or whatever you want to call it, those metering devices are not adjustable, and they change the pressure by changing the size of the pipe. And then the thermostatic expansion valves, those ones are adjustable, and it can adjust with the load on the evaporator. So, but they're both considered metering devices, and the metering device will be number 3 out of your 4 components. And number 4 would be your evaporator. The evaporator is a device for absorbing heat into the refrigeration system. The evaporator boils the refrigerant off to a vapor. The evaporator begins to superheat the refrigerant. In the evaporator, the saturated refrigerant absorbs heat from its surroundings and boils into a low pressure vapor. So the evaporator is where heat is absorbed into the system. So like I said before, one of the main things that main concept that you need to grasp in this trade is that um, there's no such thing as cold. Like, we don't create cold. We're not, we don't make cold air. What we're doing is we're removing the heat energy out of the existing air and dumping it outside. How are we removing it? So let's talk about the airflow. So when your system is running and your blower motor or your circulating motor is turning, it's doing two things. It's blowing air out of your supply vents, but it's also sucking air through your return or your intake vent, whichever you call it. Return is the more common term. So the return is where the air is being sucked in. If you ever not sure which vent you're looking at, whether it's a return or a supply, you can always pull out a dollar bill and put it up against the vent. If it's a return vent, it's gonna suck that dollar bill up against it and hold it there because it's drawing air in. If you put that same dollar bill in front of a supply vent, it's gonna blow your dollar down because it's blowing air out. So the return is sucking air in. That return air then has to pass across the evaporator coil. And that's where our heat transfer is going to take place yet again. So we have warm air coming from inside of the room, all the body heat that's being emitted from all the different occupants in that room, any appliances that might be running, just all the heat that's in that room is going to be getting sucked in through the return, and it's going to go across that evap coil. Now the evaporator coil's got 40-degree refrigerant in there, very cold refrigerant with some very warm air coming across it. So our heat transfer is going to take place. All the heat is, heat energy goes from hot to cold. So that hot air that just got sucked in is now getting all the heat energy absorbed from it to the cold refrigerant in that coil. So it's coming out of the other side as cold air. So that same hot air that just got sucked out of the room is coming right back into the room, but minus all of its heat energy. It all got sucked out. It all got absorbed by that 40-degree refrigerant that's in the evap coil. So that's how we remove heat. So we're not really creating cold as much as we're removing heat. So that's how we're removing heat from inside and dumping it outside. The refrigerant is doing that. That cold refrigerant in the evap coil absorbed the heat from the air that passed across it, and the air is coming out of the supply vents cold. That same refrigerant that just absorbed all that heat is shot straight out to the condenser, where the heat is then rejected right out into the air. How? Because the same heat exchange is taking place, the heat transfer. Inside, on the indoor coil, the warm air from the room is being absorbed into the cold refrigerant, and then the same air is coming out the other side cold. Outside, that refrigerant is now, that same refrigerant went through the compressor, and the compressor increased the pressure. So now it's a high pressure, high temperature vapor, because if pressure goes up, temperature also goes up. So that same cold refrigerant, or no, well, hot and cold is kind of relative, but so that same refrigerant that's coming into the compressor, it already absorbed the heat from the room, but in order for the outside air, which is also hot, in order for the outside air to be able to be colder than the refrigerant, the compressor has to increase the pressure, which also increases its temperature. So now that warm refrigerant that just absorbed our heat is even hotter. So when it goes through the condenser coil, the outside air could be 80 degrees or 85, 90 degrees, and it's still cooler than the refrigerant. So when that heat comes across it, it's going to absorb the heat from the refrigerant, blow it out at the top. So again, I think I kind of tend to get ahead of myself. I hope it's making sense though. But the evaporator is where we absorb heat. The condenser is where we reject heat. Those are your two coils, and those are two out of your four components in your refrigeration system. And like I said, There's more components, but they're not critical to make a basic refrigeration system. So let's talk about the refrigerant lines. The components of the refrigeration system are connected by 3 refrigerant lines: the discharge line, the liquid line, and the suction line. Let me correct myself. So they didn't mention the transphase line. So I said there's 2, and they leave the third one out. When I should have said there's 4, but they leave the 4th one out. They always talk about the discharge line, which is coming straight from the compressor going into the condenser. Then you got the liquid line, which is coming straight from the condenser going into the metering device. And then you have the transphase line that's going straight from the outlet of the metering device to the evap coil. Then you have the suction line coming from the outlet of the evap coil getting sucked into the compressor, which is why they call it the suction line. So that transphase line is the one that they usually leave out. They just consider from the condenser outlet all the way to the evaporator inlet is considered the liquid line. But a part of that line is the transphase line. And that part would be after the metering device. So liquid line. You know what? I'm gonna real quick, or did I do it already? I did. I uploaded a diagram. I'm gonna pull that up before I go any further. Where's my diagram? Go here. Here. All right, here's my diagram that I made. And by made, I mean stole the picture off the internet and then just added my labels. So here's our compressor, right? Let's just make sense out of this thing. So our compressor, it shoots out high pressure, high temperature vapor, goes through the condenser, and it starts to subcool. It starts to subcool. Then it starts to saturate and condense to a liquid, and then now it starts to subcool that liquid. So boom, now you got high pressure subcooled liquid coming out of the condenser. This is our liquid line. So what I was saying a second ago, they consider this whole thing the liquid line, but technically, to be technical, the liquid line is here. And then we're going into our metering device. So we have high pressure subcooled liquid going in, and we have low pressure liquid / vapor coming out, because 25% of this liquid flashed into a gas. So now we have a flash gas, a liquid and vapor mixture. And this line here is the transphase line, which I left out because they had, I left it out there. So I'm guilty of the thing that I'm talking about. As you see, we have liquid line labeled here. We got discharge line labeled here. We got suction line labeled here. We do not have transphase line labeled here. Not that that's all that critical, but I just don't want y'all to be left out of any of this knowledge. So that's the transphase line. That's an extra little jewel you can drop on somebody and sound smart. So this is our transphase line, and it goes into our evap coil. This is our evaporator coil. And then the liquid travels through, and then it comes out as a vapor. And now we're in our suction line. And then our suction line leads us right back to our compressor, where this low pressure superheated vapor is then pumped into our compressor, compressed, and shot out as a high pressure, high temperature vapor, starts the process all over again. This condenser coil is located outside. It'll have a fan on top, and this hot vapor that's going in will get cooled by the fan spinning up here. So as it spins, it's going to suck outside air across here from all the angles. It's going to suck the outside air in, and it's going to shoot it out the top, and it's going to be warm air because it absorbed the heat from the refrigerant, leaving it subcooled liquid coming out. Same thing over here. You're going to have your return air coming up into the bottom of this A-frame coil. This is called an A coil. It's your evaporator coil, but the design of it is considered an A coil. right up into the crotch of the A is going to be the return air going in, coming in warm, and then coming out the other side hot because it passed over these cold coils. You got 40-degree refrigerant in there. That air is going to come out of the other side a lot cooler because all the heat that was in the air coming in has been transferred into the refrigerant. And that's all we're doing. We're we got some hot vapor here, we got some cold liquid here, and this one is a perfect environment to remove some heat. This is the perfect environment to absorb some heat. That's all this refrigeration system is designed to do. Absorb heat here, remove it here. And as we absorb heat, the air coming out of the other side is nice and cool, making everybody comfortable. So the liquid line. Liquid line carries the high pressure, warm, subcooled liquid from the condenser to the metering device. Capacity changes. The capacity of many refrigeration systems vary depending upon their operation conditions. Capacity changes also produce different refrigerant flows. An increase in refrigeration capacity circulates more refrigerant. A decrease in capacity circulates less liquid. That goes back to what I was saying over here. Okay, where is it? Here. So this is your TXV. This is your sensing bulb. The more heat that we have, the more hot air we have going across this coil, the more vapor is going to build up inside of this sensing bulb. And that vapor is going to go through this transmission tube. It's going to apply pressure to the diaphragm inside of here. And when it pushes down on that diaphragm, it's going to allow more liquid to flow. It's going to let more liquid pass. So when you increase the load, or the on the evap coil, then it's going to increase the amount of liquid going into the evap coil. If there's not a lot of heat going across this coil, like let's say in a room full of 20 people, 19 of them left, and it ain't that much heat in the room being generated no more, then the return air is going to be significantly cooler. So that's going to so now that the evap coil is a little cooler, the sensing bulb is going to be sensing a drop in temperature, which is going to cause the liquid inside of it, or the refrigerant inside of it, to condense back into a liquid. And that liquid is going to collect right here. And all the vapor pressure that was in this tube is going to ease up and put less pressure on this diaphragm and allow less liquid to come through. Because the more heat you have, the more quickly it's going to boil off your refrigerant. You're going to have to let more liquid in, or it's going to boil off too quick, and it's going to ruin the refrigeration effect. So more heat, more liquid you got to let through. Less heat, less liquid we have to let through, because we don't want to flood it either. If we don't have that much heat, but we're still sending a gang of liquid through, well, now it's not going to boil off the liquid enough, and we're going to have the danger of sending liquid back to our compressor and then breaking our compressor. So you want to send just the right amount of liquid to your evap coil. So with systems that have TXVs, it can make that adjustment for you. Systems that don't have TXVs, they're considered critically charged, meaning the amount of refrigerant that is in it at the point of install is critical. Because if it's overcharged, it doesn't have a handy little metering device that'll let less liquid through when it doesn't need that much. It's just going to let it through anyway, and you're going to have the risk of slugging your compressor. So with critically charged systems, it's important to make sure your charge is correct. And when the load is really high on a critically charged system, you know, you're going to lose a little bit of capacity. I mean, it is what it is, because you don't have this TXV to allow more liquid to come through under heavy loads conditions. So meaning if those 19 people came back in the room with 2 of their friends, you know, now we got an excessive load on this evap coil. And if we don't have this guy to say, hey, we need more liquid, it's just the same amount of liquid going in, then it'll still cool, but not as good as it was, not as efficiently as it could. All right, so moving on. Other refrigeration system components. So other components that may be found on a refrigeration system include the discharge line muffler, oil separator, liquid receiver, liquid line filter dryer, sight glass, liquid line solenoid, suction to liquid heat exchanger, evaporator pressure regulator, suction line filter, suction accumulator, crankcase pressure regulator, and oil level control. All accessories that you'll find on various different units. The more larger units, commercial and industrial stuff, you'll start getting into more components. Basic like residential units usually don't have all those things. Usually you'll have your filter dryer and then your other 4 basic components, and that's usually it. You know, a couple pressure switches. But anyway, so the discharge line muffler dampens pulsations and noise created by the compressor. The oil separator removes oil entrained in the discharge gas and returns it to the compressor crankcase. The liquid line filter dryer removes moisture and impurities from the liquid refrigerant. Sight glass allows the technician to visually see the condition of the refrigerant in the line. A liquid line solenoid is an electrically operated valve used to control the flow of liquid refrigerant. The evaporator pressure regulator controls the pressure in the evaporator. Suction line filters are used to protect the compressor from contaminants. Crankcase pressure regulators are used to keep the suction pressure of the compressor from rising above the set point of the crankcase pressure regulator valve. Oil level controls are used on systems with multiple compressors that are piped into common discharge and suction headers. So those are just a bunch of different components that you'll run into. Again, a lot of it is more commercial and industrial. A lot of the smaller stuff doesn't have all of those, but you'll get familiar with those as we go along. At some point in life, when we get back into the lab, you'll get a chance to get up close and personal to some of those components. And but I go really heavy. Excuse me. I go really heavy on the residential stuff in class, and it's just because of my experience. A lot of people, a lot of you will end up starting out there, you know. And I mean, we cover it all, and the same skill set translates into any unit because it's the same system. It's the same refrigeration system, just different applications. But again, I do a lot of my teaching with the residential stuff because A, that's where a lot of people start out, and B, that's where all the side money is. So if you want to start getting into business for yourself somewhere down the line, or even just be able to fix your own system at home or for a family member, you know, that's going to be very valuable. So so we do a lot of stuff with the residential, but again, we cover it all. But so in summary, the mechanical vapor compression refrigeration cycle is the most common of all refrigeration cycles. The 4 main components are the compressor, the condenser, the metering device, and the evaporator. The refrigeration cycle is made possible by the pressure difference, which is maintained by the compressor and the metering device. The compressor increases the refrigerant pressure by squeezing it. The metering device reduces the refrigerant pressure by restricting its flow into the evaporator. The low side absorbs heat when the refrigerant boils in the evaporator. The high side rejects heat when the refrigerant condenses in the condenser. So real quick too, just another little piece that I might have left out. The reason why we want 100% vapor going to the condenser is because the substance releases more heat at a higher rate when it's condensing to a liquid from a vapor. And then the opposite is true at the evaporator coil. We want liquid going to the evaporator coil because the substance can absorb more heat when it's going from liquid to vapor. So we want liquid going to the evap coil. We want vapor going to the condenser coil. We're removing heat at the evap coil, or sorry, we're absorbing heat at the evap coil. We're removing that heat at the condenser coil. So that is it for Unit 12. I hope that was helpful. Again, you know, the refrigeration cycle is that's what we do. That's what we do. It wouldn't make any sense to talk about any of the other modules if we didn't understand this, which is why that's one of the intro modules, this, and then 130, which is the intro to electrical. But like I said, it's very important. Make sure you review this video, review your book. The book is imperative that you read it. It's going to say something that I probably didn't say, and the book plus the video equals a whole bunch of knowledge. You can tackle your review questions. So again, hope that was helpful. Hope everybody's staying safe, staying healthy, staying away from these issues out here. And I'll see y'all on the next one.